the magic of magnetism. If you ever held two bar magnets as a kid, feeling that weird repulsion or that invisible pull,
Oh, yeah.
that simple childhood wonder is driven by some of the most, truly elegant and fundamental forces in the entire universe.
It is absolute elegance. And yet, the reality of those magnets today, the incredibly powerful ones driving your EV or a wind turbine, is totally bound up in these complex, frankly messy 21st century global supply chains.
That contrast is just incredible, isn't it? From pure physics to pure geopolitics. And that's the journey we're taking today.
Right. Our mission here is to unpack the core physics, starting with Maxwell's equations, and then pivot right into the material science and, the real strategic vulnerabilities around these NdFeB neodymium iron boron magnets.
You'll walk away understanding not just what they are, but why they've become such a critical strategic asset. So let's set the stage. We know static charges create electric fields.
But it's moving charges, a current. That's the source of a magnetic field. We have to start there.
With the basic rules.
Exactly. We start at the foundation with magnetostatics, which is basically the study of magnetic fields that aren't changing over time.
Okay, when you say time independent, that sounds a little dry, but it's actually the basis for most common electrical devices, isn't it?
It's the basis for everything DC. And the key concept here is steady currents. This means two really crucial things. First, you have zero net charge density. And second, the flow of current is constant.
So no charge is building up anywhere.
Precisely. And the simple translation of that is what's happening inside a normal metal wire. You have these static positive charges, the metal ions, and they're perfectly balanced by the moving negative charges, the electrons.
The system is neutral, but the flow is everything.
That organized flow is the engine creating the magnetic field.
And the tool we use to translate that flow into a field is Ampere's law. Let's really unpack the insight there, not just the formula.
Ampere's law, most simply, tells you that if you loop a wire, you get a looped field. It relates the magnetic field, B, directly to the current density, J.
So the magnetic field you measure when you circle a current is just proportional to the current inside that loop.
It's the fundamental statement that current is the source of the magnetic field, period.
Okay, so if current is the source, what's the simplest possible example we can look at?
An infinite straight wire. It's a classic textbook case. Because of the symmetry, the field just circles the wire. You can use the right-hand rule to see the direction, and its strength falls off as 1/r.
Now, here's a key takeaway for you, the listener, right at the start. Compare that to the electric field from a point charge, which falls off as 1/r squared.
A much faster drop-off.
So the magnetic field from a current line drops off slower, just 1/r. What does that tell us practically?
It means magnetic fields from currents have a much longer reach. That geometry is incredibly useful in engineering because the field doesn't just vanish immediately. You can work with it over greater distances.
And that idea of looping a current to create an organized field, that brings us to the solenoid.
The solenoid is a practical powerhouse. It's just a wire wound into a tight cylinder. Drive a current through it, and you create this amazingly constant and uniform magnetic field inside that cylinder.
And the strength just depends on the current and how many windings you have.
That's it. It's the basis for almost every electromagnet out there.
So we've established how moving charge creates a field. Now, how does that field interact with another moving charge that passes through it?
This is where the Lorentz force law comes in. It's beautiful. The magnetic force, F sub m, is defined by a cross product. The charge q times its velocity v crossed with the magnetic field B.
And because it's a cross product, the resulting force is always perpendicular to both the direction the charge is moving and the direction of the magnetic field.
Precisely. And that perpendicularity has two absolutely massive consequences. First, the magnetic force can never change the magnitude of the particle's velocity.
Wait, say that again? It can't change the magnitude, so it can't speed it up or slow it down?
Correct. It can never do any work on the particle. It can carve its path, push it into a perfect circle or a helix, but it can't make it go faster or slower.
That is a fundamental constraint.
It is. It's central to how we design things like particle accelerators. The other consequence is more practical. If a charge moves parallel to the magnetic field,
the force is zero. Nothing happens.
Nothing. And the force is at its maximum only when the velocity is perfectly perpendicular to the field.
We should probably mention the units here. The SI unit for B is the Tesla, or T. How big is a Tesla, really?
A Tesla is a huge field. For context, the Earth's magnetic field is tiny, about 10 to the minus 5 Tesla. Superconducting electromagnets can get up to 10 Tesla or more.
1 million times stronger.
1,000,000 times stronger than the field protecting our planet.
Okay, this brings us to what might be the most profound difference between electricity and magnetism. With electricity, you have positive and negative charges, electric monopoles that can exist all by themselves.
But magnetism is different. The second key Maxwell equation for this is basically the no monopole rule. It states that the divergence of the magnetic field is always zero.
And the deep implication of that is,
No isolated magnetic charges. You can't have a magnetic north pole without a south pole attached. It means magnetic field lines have no beginning or end. They must always loop back on themselves.
so the classic experiment. I take a bar magnet, I snap it in half to try and isolate the North Pole.
And you just get two smaller bar magnets, each with its own north and south pole. The field lines just reconfigure. It's a fundamental truth.
Because there are no monopoles, magnetism is fundamentally dipolar.
Exactly. We model everything as tiny magnetic dipoles, which are usually generated by the current loops from spinning electrons in the atoms.
And this dipolar nature affects how the forces fall off with distance, right?
It does. The field from a dipole falls off very quickly, as 1 over r cubed. And the force between two dipoles, like the pull between two bar magnets, drops off even faster, as 1 over r to the 4th.
Which is why they feel so strong up close. But the force vanishes so quickly when you pull them apart.
It's it exactly.
It makes the fact that theorists still predict the existence of a magnetic monopole even more fascinating.
It's truly mind-bending. The physicist Paul Dirac showed that monopoles could exist if their charge was quantized relative to the electron's charge. And what's wild is that almost all modern grand unified theories predict they must exist.
But we've just never seen one.
Not a single one. It's a huge, tantalizing gap between theory and observation.
That's a perfect pivot. From pure theory, let's land firmly in the applied world. Because the end result of all those microscopic electron spins is the permanent magnet.
Where all those atomic dipoles are just forced into alignment to create one giant, powerful magnetic moment.
And when we talk about powerful magnets for modern tech EV motors, wind turbines, we are talking about one thing: neodymium iron boron magnets, NdFeB.
They are, quite simply, the strongest commercially available magnets on the planet, critical for the clean energy transition.
Because they let you build much smaller, lighter motors for the same amount of power.
Right. And their composition relies mainly on light rare earths, specifically neodymium and sometimes praseodymium. That's where the raw power comes from. But they have a weakness.
Heat. They demagnetize when they get too hot.
Exactly. So to make them resistant to heat, which is crucial for an EV motor that gets hot, you have to add in small amounts of heavy rare earths, or HREs. We're talking about dysprosium and terbium.
And that's especially true for the high-performance sintered magnets that dominate the market.
They make up about 93% of the market, and they almost all require some HREs for high-temperature applications.
Before we get into the geopolitics of that, let's touch on one last piece of physics: magnetic shielding. If these fields are so powerful, how do you protect sensitive electronics from them?
It really depends on the frequency. For a steady DC field, you use what we call magnetic shielding. You use a high permeability material, like silicon steel.
And its job is just to divert the field lines around the object you're protecting.
Right, it gives the flux an easy path to follow. But for high-frequency AC fields, you need a totally different strategy: electromagnetic shielding.
And that uses conductive materials, like copper.
Because the high conductivity lets you generate opposing fields through what are called eddy currents. Those currents create their own magnetic fields that cancel out the external field.
And here's a fascinating trade-off. You can't just combine them. If you use a material that's both highly permeable and highly conductive in an AC field,
you can actually make things worse. The eddy currents can end up pushing the external flux around the shield instead of neutralizing it. It's a really delicate balancing act in material science.
Speaking of delicate balances, let's talk about the global supply chain for these magnets, because it is anything but balanced.
That's an understatement.
Here's the brutal reality. The supply chain for these critical NdFeB magnets is staggeringly concentrated. It presents a massive strategic vulnerability for basically everyone.
The concentration is dramatic. Let's look at the numbers. At the mining stage, China accounts for about 58% of global rare earth production. But mining is just the start.
The real control is in the processing steps that come after.
Absolutely. China controls almost 89% of rare earth separation capacity. That's the complex, environmentally tough process of separating the individual elements from the raw ore.
89%.
And it doesn't stop there. They control an estimated 90% of the metal refining and alloying, and then 92% of the final magnet manufacturing.
So if you're a U.S. or European company building an EV, no matter where your raw ore is from, it almost certainly has to pass through China before it ends up in your factory.
That is the current reality. While the U.S. has great resources, like the Mountain Pass mine, that concentrate has historically just been shipped overseas for processing. And there's still other dependencies, imports of key ingredients like ferroboron and special steel.
Let's break down the key vulnerabilities here. Number one is the environmental hazard.
This is a huge issue. The separation processes use harsh chemicals and create a lot of toxic wastewater. And historically, a massive chunk of the heavy rare earth supply, maybe up 65%, came from illegal mining in China with zero environmental standards.
Which drives down the global cost and makes it impossible for responsible producers to compete.
Exactly. Then there's the second vulnerability, intellectual property.
Patents.
Right. For decades, key patents held by Hitachi on how to make high-quality sintered magnets were a massive barrier to entry. Many of those are expiring now, which is opening things up, but it locked out competition for a long time.
And then there's just the sheer scale of demand. What happens in a major supply disruption?
The risk is overwhelming for the civilian sector. Military needs are actually pretty small, but for EVs and wind turbines, the demand is huge. A disruption would mean an immediate shortfall equivalent to half a year's output from a major magnet plant.
So that would grind the clean energy transition to a halt.
It would be immediate, severe economic pain.
So mitigating that risk isn't just about building new mines, it's about engineering our way out of the problem.
Correct. It means finding ways to reduce the amount of those scarce, heavy rare earths we need. There are techniques like grain boundary diffusion, which just coats the magnet grains with HREs instead of mixing them all the way through.
Using less material to get the same effect.
Exactly. And also substituting in more common rare earths, like cerium, to conserve the really critical elements.
What an incredible journey. We started with the elegance of Ampere's law and the mystery of the magnetic monopole, moved to the microscopic spins that create these powerful magnets, and we've ended up right in the middle of a global supply chain choke point.
And if we loop back to the physics for a final thought, remember that unique constraint of the Lorentz force law we talked about.
The magnetic force is always perpendicular to the particle's velocity.
Which means it can't change the particle's speed, only its direction.
So we can't just make a magnet stronger by speeding up the electrons.
We can't. The only way to meet this soaring global demand, given the very real resource limits, is through breakthroughs in material composition and engineering design. The physics itself sets the boundaries.
So here's a final provocative thought for you to explore. Considering this massive projected demand for EVs and offshore wind, and knowing that a motor's power is fundamentally constrained by its materials, how might these limits force us to invent completely new, maybe even non-magnetic solutions in the coming decades? We invite you to explore that fascinating intersection of material science and electromagnetism further.